Welcome. In this video we continue our unit on functions, and in particular we really focus on the graph of a function, looking at what kinds of information we can draw from the graph and some of the properties that graphs have. We will look at 4 objectives in these 2 sections. In 3.2 we will look at identifying the graph of a function and obtaining information from it. And in 3.3 we will look at objective 3, using a graph to determine where a function is increasing, decreasing, or constant. And 7, finding the average rate of change of a function. It looks like we're bouncing around a little bit, but these ideas really are closely connected to each other. Alright, so let's talk about the graph of a function. One of the things that is really useful to us is called the vertical line test, and this will tell us whether or not a graph that we're looking at is actually the graph of a function. So look here are 4 graphs. These are all graphs of equations. So underneath each graph you can see the equation that gives us the graph. Some of these are functions and some of these aren't. I mean, where y is a function of x. So in which of these pictures is y a function of x? And we can tell by using the vertical line test. The vertical line test. A set of points in the xy plane is the graph of a function, that is, y is a function of x, if and only if every vertical line intersects the graph in at most one point. So the graph on the left, yes, that looks good. And then the second one, graph B, check, looks good. It passes the vertical line test. But C, no, that vertical line cuts it in 2 places, so not the graph of a function. And D, no, that vertical line crosses the graph at 2 points, so not the graph of a function. And the idea is one x can correspond to only one y. When I put in one x value, only one y value can come out. But look what's happening here in that third graph. That one x value of a positive 1 is giving me 2 different y values, a positive 1 and a negative 1. And the same kind of idea is going wrong in the fourth graph. Let's talk about what kind of information I can pull out of a graph. So on the right, you see there is the graph of a function, and we'll say that's the graph of a function f. What can I tell about the function f? I can answer a lot of questions. So let's go through these questions and see what I can answer. So first of all, A. What is f of 0? Well, f of 0 is going to be the point on the graph 0, something. So let's look to the graph. And I see 0, 4 is on that graph. So f of 0 equals 4. How about the domain of f? So those are all the x values where the function is graphed somewhere, and it looks like it starts at 0, and those x values go all the way up through maybe 7 pi over 2. So the domain is going to be 0 all the way up through 7 pi over 2. And I use brackets on both sides because I do include the 0 on the left and I do include the 7 pi over 2 on the right. How about the range? So those are all the possible y values that I can get out. Let's see, the lowest y value looks like it comes down at -4, and the highest possible y value at +4. So how about -4 to +4? Is there a y-intercept? What do I mean by y-intercept? That's where it crosses the y-axis. And just a nice observation, it crosses the y-axis when x equals 0. So to find the y-intercept, I figure out where is x equals 0, and when x equals 0, it looks like it crosses at 0, 4. So the answer to the question, is there a y-intercept? The answer is yes, there is, and it is at the point 0, 4. And E, are there any x-intercepts? And the x-intercepts occur when y equals 0. So that is when they cross the x-axis. And it looks like I have 4 of those things. All right, let's list them out. So there are 4 x-intercepts, and these are all the points that have 0 as the y-coordinate. All right, F. Oh, I forgot to keep circling my letters here. F. For what values of x does f of x equal 4? So basically we're asking, when is y equal to 4, and I see 3 points up on the top. Those are the 3 points where my y value equals 4, when f of x equals 4. And what are those corresponding x values? So it looks like 0 and 2 pi and 4 pi. And then lastly, g. For what values of x is f of x less than 0? So let's see. In this case, we're looking at the parts of the graph that dip below the x-axis, and so these two u areas. Well, let's focus on this first u area. So it starts off with an x value of pi over 2, and it ends at the value of 3 pi over 2. And as an interval, I'm going to use my parentheses, because I don't actually want to include the pi over 2, because at pi over 2, f of x equals 0, but I really want f of x strictly less than 0. So as long as my x is just a little bit more than pi over 2, then I'll get a negative value. Let's see here. And, I was going to write and, but maybe a fancier way to write and is with the union symbol. The next segment, so going from 5 pi over 2 all the way up to 7 pi over 2. So there we go. There's a lot of information that I can draw about the function just from looking at the graph. Now, let's go in the opposite direction. Let's get information about the graph of a function. So here, this function f is given to us symbolically. F of x equals x plus 1 over x plus 2. What can I figure out about the graph of this function? So here are some questions. Let's try to answer this. What is the domain of f? So we've looked at problems like this already, and I know that the domain is everything except, in our case, here, where the denominator is 0. So everything except negative 2. So maybe B. Is 1, 2 a point on the graph of f? This is really asking the question, does f of 1 equal 2? Well, what is f of 1? F of 1 is, let's see, when I put 1 into the numerator, I get 2, and when I put 1 into the denominator, I get 3. No. So the answer for B is no. But now I have discovered a point that lies on the graph. It's the point 1, 2/3. So when I graph out this function, the point 1 and 2/3 will be on the graph. C. If x equals 2, what is f of x? What is the point on the graph? Oh, so really we just need to figure out f of 2. All right, f of 2 equals 3 over 4. So there's a point on the graph, 2, 3/4. D. What is the y-intercept of the graph? So remember, this is when x equals 0. That'll make, so the point, I guess, if I plug in 0 for x, 0 plus 1 over 0 plus 2 equals 1/2. So there is a y-intercept, and the y value is 1/2. I guess I could write this as a point, 0, 1/2. And E, are there any x-intercepts? So this is when y equals 0. I'm using y, but another way of saying that is f of x equals 0. So f of x equals 0. So then I need to figure out x plus 1. This whole expression over x plus 2 equals 0. Are there any values of x that I can plug in and make this work? Oh, I could multiply both sides by x plus 2. And if I do that, all I end up with is x plus 1 equals 0. Oh, subtract 1 from both sides. X equals negative 1. And that makes sense because originally, looking back at my function, if I were to plug in a negative 1 into that numerator becomes 0 and the whole function becomes 0. So x-intercept at the point, negative 1, 0. Looking at a graph, often it's helpful to be able to determine where the graph is increasing or decreasing or being constant. So let's focus on the interval negative 2 to 0. So on the graph, here is a negative 2, there's 0, so I've highlighted it in red. I'm focusing on this little segment in the x-axis. What is going on with the function just over that interval? The function starts at a y value of 0 and increases up to a y value of 4. Well, I just said it in the words there. It increases. So over that particular interval, the y values are increasing. My function is increasing. Let's take a look at a different interval. So what about the interval from 4 to 5? So I will highlight that in red, 4 to 5. And over this interval, I look at what the function is doing, and as x moves from 4 to 5, the y values are decreasing. And so this function is decreasing over that particular interval. How about the interval from 0 to 3? So 0, 3, I'm highlighting this segment on the x-axis, and when I look at the graph is constant, and there's the answer to our question. On the interval from 0 to 3, the function is constant. So functions can be increasing, decreasing, or constant over various intervals. Oh, there is one more possibility. Say over, how about the interval from -1 to 6? It isn't any of these things. From -1 to 6, it's doing all three, increasing and constant and decreasing. So there's no one thing that it's doing over this interval. Sometimes you see questions like this, where a function is given and it says, list the intervals on which f is decreasing. There are infinitely many intervals, but we're really looking for the largest possible intervals. So let's look at the graph and identify the parts of the graph where the function is decreasing. I see two segments. This segment on the far left is that's one segment where the function is decreasing, and also the segment on the far right. That's another place where the function is decreasing. So what I really need to do is identify the intervals on the x-axis. So on the left, it looks like the x values there go from -6 to -4. -6 to -4. And for the segment on the right, it looks like maybe those x values go from 3 up to 6. So that's the answer to the question. Let's talk about average rate of change, because it's great to identify parts where a function is increasing or decreasing, but now we're going to answer the question, how quickly is it increasing, or how quickly is it decreasing? We're finding average rate of change. This is an important idea that comes up often, and we talk about this a lot in calculus. The formula for the average rate of change. So take a look at this function. This is the function f of x equals 1/2 x squared plus 1. And from 0 on up to the right, as x starts at 0 and moves to the right, the function is increasing. But it increases at different rates. At the beginning, the function is increasing slowly. It has sort of a shallow curve there. As I move to the right, the y values don't increase very quickly. But later on, the function increases much more quickly. As I move to the right, those y values go up and up and up, faster and faster and faster. So at some points of the curve, the function increases slowly. At some later points of the curve, the function increases more quickly. I might want to know, from x equals 0 to x equals 4, how quickly does f increase on average? So I'm sort of looking at this point when f equals 0, and when f equals 4, I'm looking at that point. And so the function, how does it, on average, how does it change between those 2 points? And here's how we figure it out. I imagine that between those 2 points there's a straight line. And that straight line is kind of like straightening out the curve of the function. And so instead of looking at the curvy function, which is a little bit complicated, I'm just going to look at that straight line and say, how does that straight line change from those 2 points? And here's how we do it. I'm going to figure out basically change in y over change in x. The y values have changed. by a certain amount, and I can figure that out. That's my f of 4 minus f of 0. That's how much the y values changed. And the x values changed a certain amount also. How much did my x values change? Well, that was 4 and 0. So by figuring that out, I get 9 minus 1 over 4. That's 8 over 4, which is 2. So that tells me that this function is changing on average by 2. Well, 2, what does 2 mean? That means that for every little change in x, it's going up by 2 units of change in y. So I go over 1 unit in x, and it goes up 2 units in y. Over 1 unit in x, and up 2 units in y. The average rate of change of f from 0 to 4 is 2. Here's the idea in general, thinking about the formula for the average rate of change. I have a function, y equals f of x, and I have a graph, and I want to know from a to b, what is the average rate of change of this function? The average rate of change of a function f from a to b is f of b minus f of a divided by b minus a. There's our formula for the average rate of change over an interval. Well, let's talk about a secant line, because I do have a line going through here, and it seems like this calculation really depends on the line. A secant line is a line that goes through 2 points of a curve. So that's exactly what we have. We've created a secant line to help us figure out the average rate of change of the function. But in fact, this calculation for average rate of change of the function, that is the slope of the secant line. So these two ideas are basically the same thing, the average rate of change of a function and the slope of a secant line. If you can figure out one, you have just figured out the other. Let's do some examples. Here's a function, f of x equals 3x squared minus 8. What is the average rate of change of f from 2 to 5? So the formula says I'm going to take f of 5 minus f of 2 and divide by 5 minus 2. And then we can work out f of 5. I plug it into my function. F of 5 equals 67, and f of 2 equals 4. I do the calculation, and it turns out that 21 is my answer. So what does that mean? That means that as x changes a little bit, my y is going to change 21 times as much. So if x increases by 1, then y increases by 21. Every little step in x to the right in x is matched by an increase of 21 in the y direction. It's very, very steep. This thing seems to grow very quickly. For this next question, what is the average rate of change of f from -3 to 0? Pause and try. Pause the video, give this a try, see if you can work out the formula and get an answer. Be careful with those negatives, and then unpause the video when you are ready to check your answer. Okay, give it a try. Okay, so let's check out the answer. It turns out I can do f of 0 minus f of -3 divided by 0 minus -3. F of 0 is -8. F of -3 is 19. So -8 minus 19 divided by 3, that gives me -27 over 3, which is -9. So -9, that's a negative. So actually think about it this way. For every little change in x, I'm actually dropping down 9 units in y. Or as my x increases by 1, the values of the function decrease by 9. Alright, now let's think about the secant line. Find the slope of the secant line connecting 2 f of 2 and 5 f of 5. So these are points on the graph of the function, 2 f of 2, 5 f of 5. But in fact, what points are they? They are the same points I had on the left. So I can figure out change in y over change in x, and it's exactly the same calculation that I had from before. So take a look at that and really see that you understand the connection there. And then the last question. Give the slope-intercept equation for the above secant line. Slope-intercept. So slope-intercept is y equals mx plus b. Well, I have the m. I know 21 is the slope. I need a b, which is my intercept, which I don't know. But I do know 2 points on this line, and maybe I can choose one of them, maybe the point 2, 4. And we can start with the point slope formula. So there's the point slope formula. I have a point, 2, 4. I have a slope, 21. So I plug in the 2 and the 4 where they go. I plug in the 21 where it goes. Let's distribute the 21 on the right. And then I will add 4 to both sides. And we get it. So there's our answer. Y equals 21x minus 38. That is the slope-intercept equation for the secant line. And that concludes this video where we have talked about the graph of a function. There's lots of information that we can pull out about graphs of functions.